So I'm going to talk about the future. I have an optimistic view of the future, and I hope you'll share that with me when I'm finished. But I'm so optimistic that I feel obliged to do two disclaimers. The first is the legally required disclaimer, because our earnings announcement is this week, and I don't want you to go off and buy or sell Intel stock because I jazz you up so much. Secondly is really my own personal disclaimer. I'm in the prediction business and have been for a while, long enough to make lots of mistakes along the way. And so I'm going to do a brief look back to give you a sense of what I was talking about 10 years ago, what I was talking about 5 years ago, and do a little bit of scoring before I launch into what comes next. So 10 years ago, I might have shown a foil something like this on the left. This is, of course, the cleaned up public version, not the messy internal version that we always carry. If I go back and I look at the internal version, 10 years ago, I basically said, hey, it's all about materials. 80% of the projects that we had on our research roadmap at that point in time were related to building materials into devices, building new materials into interconnects, looking at novel functions along the way. And interestingly enough, the remaining 20% that were around dimensional control were typically using chemistry. Atomic layer deposition, atomic layer etch, directed self-assembly, all the things that are using materials to get to a different place on an overall dimensional scaling curve. So what did I get right? Well, I think directionally that's still true. Materials is one of the most important things that we continue to work on. Focusing on chemistry to do better dimensional control is one of the key things that we're working on. What I got wrong is perhaps clear in hindsight. Whenever I put one of these things out, people take it really literally. So as a cleaned up external version, people said, oh, well, let's measure where that box is on the chart, and that must be a precise prediction of what's going to happen next. Or, this looks so simple, industry's got it. Those of us in government, we don't have to do anything. We don't have to do anything except ride the curve of industry progress. And I'll draw your attention to something down at the bottom here, my footnote, where I basically said, well, we can't see past 2020, and people took that literally as the world ends in 2020. Now, obviously, we don't believe that. It was a statement of how far we can see and not a statement of when the world ends. But generally, directionally, this is right. The timing of a lot of these things are imprecise. So let's move forward about 5 years. I would use a much longer version of this if I were in a technical audience, but this is a simple version that basically says, hey, the new Moore's law is the center here. There are three things at the top: continued CMOS scaling, in the middle, a move to 3D, and at the bottom, adding novel functions. And that would still be true today. On the outer sides, I've got new ways of physically building products, and I have new architectures for products. The idea was we were going into a heterogeneous future. It was not going to be one size fits all, and that would still be true today. So directionally, I think I did get this right. Of course, the details are things to be worked out. From a timing point of view, the novel functions are a bit slower than my internal projections were at this point, but the heterogeneous architectures is actually happening faster than I projected. So I'll summarize the past messages of, scaling is really about materials, and we're not limited by physics so much as our ability to build things precisely and control the dimensions of them. We have new opportunities on the horizon around increasing integration, novel architectures, and of course, connectivity. We can't view things as simply monolithic systems that only do something by themselves. They have to be part of an overall system of connections. And then finally, Moore's law continues, but it's evolving. Now let me jump forward and look into essentially the production pipeline. And you can see what's happened as a product of those directions for research. So first of all, regardless of where a company names their nodes, all the companies are showing similar progress. They're introducing novel ways of engineering devices, represented here by strained silicon on the left. They're introducing new materials, represented by high-K metal gate in the middle. And they're going to 3D, FinFETs, Tri-Gates, whatever you choose to call them. And we still have visibility out beyond where we're at now. The world doesn't end in 2020. We've just pushed out the horizon of visibility a little bit further. So, do we expect this to continue? My answer is yes. So if I look into the research pipeline, this is a very complicated chart that is part of a set of benchmark activities that's co-sponsored by the NRI and the StarNet program. They've been doing this for about 5 years. I'm not going to go into the details here, but to give you a sense as to what this represents, this is for a conventional logic. It's a 32-bit adder circuitry. The two axes represent performance and energy, and you would like everything to be at the lower left as the best point. There's a lot of things here. There's a zoo of devices that people are working at. This could not have happened without a combination of academic, industry, and government participation. Individual academics can't work on all of these things. Individual companies can't either. Governments have different long-range perspectives than individual companies will. That partnership allowed this activity to take place, and the benchmarking allowed further progress from a research point of view in really 3 different areas. First, improving the efficiency in switching. That's easiest to tell by looking at the dots that are connected by the dashed lines. They are moving orders of magnitude better from a switching efficiency point of view, mainly by changing materials and changing how the devices are put together. We realize from a circuitry point of view that electronic interconnects are probably going to have to be required as opposed to spin interconnects or other types of interconnects. And so figuring out how to efficiently transform from spin to current and back again is part of this progress. And we have a much better understanding of logic circuits and how these novel technologies interact with novel data processing. So this particular one is for conventional electronics. There are similar charts that are available for novel data processing, and in many of those, the novel devices do considerably better. I want to point out one last thing before I move on. The green dots that are sort of in the middle of the lower left are CMOS. Not the CMOS we can build today, but the CMOS we believe we can build in a few years' time. And so CMOS is not worse than all of these, nor better than all of these. It's somewhere in the middle. And we believe the future will include CMOS along with novel devices and novel functions. So, boiling down that previous chart into a simplified form, we have 2 major areas that are working on. One is we're looking at devices that have very steep on-off characteristics or are non-volatile. That's really going after the power part of the performance. We're also looking at things that are novel from a logic point of view. There are technologies that allow us to process more than 1 bit of information at a time. There are things that allow you to do more efficient circuitry to do data processing. Both of those will allow us to leapfrog where we can get to with CMOS. But as I said on the previous page, there is still a role for CMOS. So we're really looking for technologies that can be built up in stacks, technologies that can use CMOS for what CMOS is good for, the other technologies for things that they're better for. This is a direct continuation of that 3-item column that I said is the new Moore's Law going forward. And we continue the research. So yesterday was a long discussion around the jump centers. The novel architectures are represented at the upper right in the CBRIC Center. The novel devices are represented down at the bottom here on the right in the Ascent Center. And there are a lot of other things related to how do you do integration both at the architecture level as well as novel kinds of technologies. Through the SRC, We've been able to do this for multiple decades, bringing together academics, industry, and government together and work on some of these hard problems that we can't solve individually. And so we expect that this will continue. But now I need to take a moment and talk a little bit about economics. As technologists, we like to ignore economics to our detriment. If I go back and I look at the original Moore's Law paper, he was making an observation about memory technology, and he really only was talking about electronics. Yes, he did talk about a lot of things, but the observation itself that has become known as Moore's Law is really that top edge of this triangle. It relates cost per function or price to integration or features. It came later. Dennard observed MOS transistors scale at a particular rate. That observation was 1974. Moore's observation was in 65. It related to feature scaling and device performance. So it's the left side of this triangle. And then there's an architectural observation. I've chosen Fred Pollock, who's from Intel, an observation made in the early 90s that if you double the area or complexity of a CPU, the performance went up by the square root of 2. Those three things together have come to be known at Moore's Law, even though technically Moore only made the observation of economics. And so if someone says Moore's Law is dead, they might mean the economic piece. They might mean the device scaling piece. They might mean the architecture scaling piece. And you have to drill down one more level to understand for sure. If someone said Dennard scaling is dead, I would say yes, Dennard scaling's been dead for 15 years. We deviated from that a long time ago, and we've made up for it by putting performance boosters like strain silicon and high-K metal gate, and the world keeps turning. People may say, well, Pollock's rule is dead, and I'd say, yes, I agree. We've deviated from Pollock's rule for 15 years. We've made up for it other ways. A rule that is about one set of workloads with one specific architectures is not expected to last as long as an economic observation. If someone said the economics of Moore's Law are dead, at that point I would challenge them. However, there is an economic point that is not clearly captured in usually the writings about Moore's Law, which is the cost of doing the upfront engineering. Moore's observation was really about the production cost once that engineering was done. And so yes, there is a challenge with economics around that upfront cost of doing a design. But I want to show a point of how economics trumps technology. And so I'll start with the observation that DRAM latency is not scaling. This is not a new observation. We continue to improve on bandwidth. We continue to improve on power. We continue to improve on density. Those are all economic things that are favored by Moore's Law, but latency is not one of those things. Latency is really performance-driven. And from a technology point of view, we know how to build lower latency DRAMs, but they're less economical. This is one example of something that causes a deviation from Pollock's rule. If you're limited by memory latency, your performance will not increase as much. And there are other equivalent things. If your network is the bottleneck, your performance will not increase as much. So there's more to it than this, but this is an example where the technology is known, but the economics don't favor it. Let's flip it. Let's talk about the ability to scale lots of information into a very small space. This was an announcement of a 96-layer 3D NAND, that theme of building up in 3D, with 4 bits of information equivalent per cell. So we've increased the amount of information density because economically it makes sense to do, even though from a technology point of view, this is orders of magnitude harder than that DRAM latency problem, because the economics favor it. It's also a good example of post-Dennard scaling. This was done without feature scaling at all, and yet we were able to pack more information. So the takeaway is not that only things that are economical will get done, but there are opportunities for partnerships to offset the economics. We need to be mindful of the economics. We need to work on it at the right point in time. The research collaboration is an example of using a partnership to overcome the economics of, let's say, an individual company trying to sponsor all the research in the world. So as we look forward, looking for partnerships at the right stage to overcome the economics is an important part of that. Now, what is industry going to do, more or less regardless of whether the technologists want it or not? Well, we have three views of the future here. They're all going to happen simultaneously. People are going to demand better devices. In this context, device means something that a human interacts with. Humans are very limiting. You know, your eyesight is only so good. Your ability to handle complex interface is only so limited. Your fingers are a certain size. You demand things that are convenient. You demand things that are consistent. So all of these things will happen, but that will make constraints on the technology choices that will go into it. One of my counterparts, a CTO in another industry, was lamenting the fact that we were spending too much time on mobile devices when we really need to be working somewhere else. And I happened to look at his personal device, and he had a BlackBerry. He was happy with it. But many other people don't. So we'll continue to work on those. In the middle, ambient computing has a different set of constraints. You no longer have that need to have consistency and complexity of interfaces. You have different constraints, perhaps if they're battery operated, different constraints from a reliability point of view. But this is a big market as well. This will happen. And then finally, the cloud is an interesting case where we're trying to collect essentially as much information as we can, as much data as we can, turn it into information, turn it into decisions. And even a workload that is a relatively small fraction, when multiplied by a very large ecosystem, makes things worthwhile. This is a place where you can do novel architectures because the market becomes big enough to support them. And so again, industry will do this. So from a technology point of view, we will continue to integrate and lower the cost per function. It makes economic sense. And oh, by the way, that's Moore's law. We will continue to find ways to manufacture with both precision and control because it makes economic sense for us. We will support emerging workloads once the market is big enough. We will continue to do power reduction for these portable devices that people insist on carrying around with them. And we'll be able to do compute at scale. All of those things will happen. But you won't be able to predict in advance exactly which technologies. You won't get to pick and choose which technologies. So what if you have a favorite technology you think is good for something, but industry doesn't support that because the market's not big enough? Well, so that's part of the discussion. How do we find a path forward? And for that, I think a useful metaphor is to think about oceans and islands. In this context, an ocean is a representation of a big market, general purpose product. Think CPU, GPU, whatever. And that performance level, the equivalent of the sea level, rises over time. It continually gets better. An island represents a special purpose product. Now, obviously, if the island doesn't stick much above the sea level, you're probably better off not doing it. But if you have a sufficient demand and your island is big enough, building a special function product makes sense. And the job is to be sufficiently better. Typically, people talk about 10x, 100x better than the general purpose. Then you have a market. But it doesn't have to be a choice. Why not use both together? So let me give an example. Here I'm going to say the CPU is the ocean, and the FPGA in a given configuration is the island. And in this case, I'm building a system that I can do reconfigurable compute. The CPU is very general purpose from a programming point of view. You can write as inefficient code as you like. and use all the tools available, but there's certain things that won't run very fast, in part because of that. You can configure an FPGA to do a particular workload. And for something like AI, where the algorithms are evolving very rapidly, this makes an interesting choice. This combination makes an interesting choice of how to support that kind of workload going forward. So let's extend that. Let's say CPUs and FPGAs are both Ocean products. Can we add other things to it? Well, yes. And so the goal of CHIPS is to standardize, to find a way to combine multiple best-in-class elements without making each best-in-class responsible for doing all of the general purpose things that are required to make a useful system. So we want to address this at multiple levels. Part of that is figuring out among our community how to cooperate on how to connect things together. And there was an announcement today around that. Part of it is figuring out how to assemble the IP in a modular way so that we can improve the overall time to market. Part of it is generating reusability so we can improve the overall engineering efficiency. And there's a collection of people working on this already, more than I have on this page, and we're actively engaging more partners as we can. So, are we done? Well, no, we've constructed essentially the first level in this overall hierarchy. Let's imagine I've got a researcher who says, hey, in the cloud, I see a particular kind of video, it's appearing over and over again. I can build an accelerator to go with that. Connecting it at the physical layer, connecting it at the protocol layer is only the first step, and there's more to it than that. There's a view of how does the programmer see it? Is it an optional component, not an optional component? Is it an extension of a language you're used to? Do you have to write special functions? Do you have to address through a call library? All of those things need to be addressed. There's a security aspect. Whenever we make a system more complicated, monolithic or not, we have to consider whether one piece of the system can be used to attack another. We have to consider whether we've created a side channel unwillingly along the way. And then finally, there's a system administrator point of view. Things as simple as, can you boot up the device? Can you do hot swapping? Things of that nature. My understanding is there are future programs in the pipeline that will be addressing different aspects of this. I think there will be more details coming up after me. So this is a way forward, but it also requires us to think about things differently. So we're used to thinking about hardware as being hard and difficult to change, and all of that is true. But the reality is we spend a lot more on software than we do on hardware. And as was talked about earlier, we try to make things efficient for the programmers, which doesn't necessarily make things efficient from a run point on the hardware. So as we think about novel architectures, people say, well, how do you program it? And sometimes that is the wrong question. And so as an example, deep learning is a system where you start with essentially known labeled data. You're constructing the equivalent of a program by doing training. And so rather than spending time writing code, you're spending time cleaning, labeling, creating that data set along the way. And so your focus has shifted from one place to another. If I look at something like neuromorphic, particularly in this messy, tangled, recurrent format here, it's a real-time machine. Even if nothing is happening, that is the equivalent of an experience. So figuring out how we can create the right experience to create the right procedures to operate correctly, that's a hard problem. That's something that we're going to have to continue to work on over the next few years' time if we really want to get to the point of having lifelong learning machines. And then still further out is quantum. And quantum is simply weird when you think about it from an algorithmic point of view. It's equivalent to dumping in a whole bunch of answers that you think might be the answer and then having the right procedure to extract that out. An interesting challenge for us now at this stage is we have very limited, noisy quantum systems. And finding the optimal algorithm that works under those constraints is difficult. And so we're spending as much effort figuring out algorithms as we are trying to build physical hardware. So, in summary, what are the key points? First, we have to think about the system. We can't build components and then figure out how we're going to put them together in a system. We have to be thinking about what the end system looks like, and it may be many systems along the way are going to do, what application they're going to do and how they're going to work together. Moore's law has evolved and will evolve. Moore made the observation that no exponent continues 20 years ago, and the world didn't stop turning. You know, Moore has been surprised many, many times by the ingenuity of people working on it, and we expect that that will continue. Materials, novel devices, and 3D are the key things now. In 10 years' time, there may be a different list. And then finally, commercial markets will find solutions. The economics are there. If we have the right partnerships and the right heterogeneity, we can work on opportunities that are outside the realm of the ocean products, the mass market appeal. And so I think the future is bright. I think we have a lot of opportunities ahead of us. I think there are more challenges, but also more options and more opportunities as we look forward. Thank you very much.